Today, I'd like to talk to you guys about comparisons of dynamics data analysis methods. This project, Juan Guerra and I worked on together this summer with our mentors, David Hogg, Adrian Price-Whelan, Chitska Starkenberg, and Emily Cunningham. So this project, we wanted to use kinematics to infer the galactic structure. So we wanted to connect a single snapshot in time of kinematics to inferences about things like the dark matter distribution. And so we spent this past month implementing and comparing ways that we could do that. So basically, we wanted to constrain the galactic gravitational potential. And to do that, you need some data and a data analysis method. So briefly, I'd like to just introduce you to some of the methods that we considered this summer. You'll hear more about the methods that I don't discuss in this talk in the next presentation, which is Juan's talk. But for Jean's equations, one advantage is that there's no explicit distribution function, so there's no explicit functional form that you need to use this method. But a disadvantage is that you have to know something about the underlying distribution of your population. For orbital torus imaging, that's not necessarily, like, you don't need to know your selection function. However, you need to know information that's in addition to the kinematics, which is the chemical abundances of your stars. For Schwarzschild modeling, there's, like Jean's equations, no explicit form of the distribution function, but as Juan will show you in his talk, your orbit libraries can become insane, like, pretty quickly. For stream/spiral fitting, we didn't really get to this summer, but I know like Adrian and Robin Sanderson have done work on this. The good thing is that there's an explicit likelihood function that you can use. However, you again run into selection effects. And for virial theorem, you're working with simple equations. However, it's really only useful for certain potentials, which are power laws. So this is a gigantic table, and what I really want to leave you with is the impression that each of these methods makes different but always strong assumptions, and each of these methods are differently sensitive to violations of those assumptions. So the method that I primarily focused on this summer was orbital torus imaging, and motivation for this method was found in the existence of chemical abundance gradients from real data. And so this plot is just showing you abundance gradients for 8 elements for a sample of 56,000 red giant branch stars, which have high quality apogee and Gaia data, and these are found in the Milky Way disk. And so this paper is from the 2020 paper by Adrian, David Hogg, Catherine Johnston et al., which is the original paper that outlines this method. So shifting from the real data, the data that we worked with in this project was toy data, and it was a 1D system. It had an isothermal distribution function, and that was embedded in a simple harmonic oscillator potential. We had 10,000 tracers whose positions and velocities were sampled from Gaussians, and since we knew the potential, we could compute actions and angles from them, and we made our metallicities, which are fake metallicities for our toy data, a function solely of those actions. So we built toy dynamical models for toy dynamical systems. We observed them, and then we implemented different methods and compared how they stacked up against each other. So I've been saying the words orbital torus imaging at you for like 3 slides now, and so I want to take the time to slow down and talk about like what that means. So orbital, of course, refers to the orbits of your stars, and the torus is simply the space in which you find those stars. So for our toy system, we defined this relationship between the metallicities and the actions such that the metallicity varies systematically in action, and will recreate the observed abundance gradients found in real data. So on the left is that relationship in the correct potential, and then in the center panel, we're looking at the mean metallicity in voxels of VZ and Z. And if you look at the center of that panel, you'll notice that the stars which have a lower absolute value of VZ and Z, they correspond to a lower action, but they have a different metallicity than the stars which have a larger absolute value of VZ and Z. And that's important because orbital torus imaging will exploit the information that's in those abundance gradients. So on the right, I've plotted 10 orbits in action angle space colored by vertical phase. And what I think is really cool about this method in particular is that you can look directly at the orbits because the stars would share the same Schmedellicity distribution, will correspond to the same action and therefore lie along the same orbit. So another thing I'd like to talk to you guys about is the Schmedellicity distribution in angles. This is important because orbital torus imaging works for a system that is well phase mixed. And so if you look on the diagram I drew on the left, you see that for a regular orbit without resonances in the correct potential, we expect it to look something like the blue circle. But if like in the incorrect potential, in a squashed potential, it'll appear more ellipsoidal because when you change the potential, you're altering the space in which things traverse. So that leads to a non-uniform distribution in angles, and this is why we expect to see a clear signature in the data, and we do. So in the middle panel, what's on the y-axis is the Schmedellicity deviation, which I've defined to be the Schmedellicity of a star minus the mean Schmedellicity of its 8 nearest neighbors in actions. And then that's plotted against theta, which are angles, and you'll just see it's a flat, like uniform distribution in the correct potential, and compare that to the analogous plot on the right for the incorrect potential, in which we see a clear m=2 signal in the data. So here, delta of theta z is just the smooth model, which I fit to the data I showed you on the previous slide in the correct potential. And this was chosen because you can always uniquely decompose your distribution in Fourier space. That is, there is one set of amplitudes and phases that describe your distribution. And so how the panels on the left relate to that is they're the coefficients of that Fourier expansion in theta z plotted against omega. But what I want you to take away here is that the dependence that the Schmedellicity deviation has on angles is 0. And that's important because going back to the actions and angles that we computed from positions and velocities, we remember that the action is time invariant because it's just an integral of motion, just like energy or the z component of angular momentum. And our Schmedellicities were defined to be solely a function of actions. And so while the angles do have a time dependence, the Schmedellicities are not dependent on that. So we want that dependence to be 0, and we see that it is. It's minimized at the correct value of omega, which is approximately 1. And then bootstrap resampling 12 times gave me a value of omega true is 1.00 plus minus 0.004, again, based on 10,000 tracers. So that was really exciting for me. And then, so the original paper does say that there is a different approach you can take, which will produce likelihoods that you could use in Bayesian inferences. However, it doesn't explicitly show it. So this summer, with the help of my mentors, I was able to take the first big step to the first ever Bayesian implementation of orbital torus imaging. So what that looks like is you start with this probability of your Schmedellicity distribution given the correct action, and within the action is embedded our potential parameter omega, since it's just defined to be as the Hamiltonian over omega, the energy over omega. We have our nuisance parameters A, B, and sigma. And so what all that is just a normal distribution with the mean as your model for how the Schmedellicity depends on the action, and the standard deviation is sigma. And so that defines our likelihood function. However, it's more useful for us to work with the log likelihood. So we take the natural log of that and optimize it. So again, these are the steps filled out again. You have your probability of your Schmedellicity given the correct action. You input a noisy model of the action to Schmedellicity, and then you optimize your log likelihood function to get your parameters. And so I'll just draw your attention to the bottom right-hand corner where we see that the estimated omega is in fact the true omega. It's 1. It recovers the correct potential using this method. So my next steps for this project include redoing the Bayesian analysis for a couple different cases, checking the case in which our system is self-consistent, also in which we add a quartic term to our quadratic potential. This is interesting because it will lead to a transition in the potentials where you'll first have like tightly bound orbits, such as thin disk stars, and then move to more loosely bound orbits like halo stars or disk stars. I want to consider how scaling affects my results. So maybe if I downsize my sample, do the error bars grow accordingly? Also, it's important to remember that we worked with toy data with no uncertainties. And so there's a lot of ways in which real data looks different from that. So it's worth asking, how strongly does us recovering the true potential depend on knowing what our selection function is? And last but not least, I'd like to apply this method to the fire cosmological simulations. I think a couple advantages to that would be that the data sets have no observational noise, and we have a fully characterized potential. And so we can see how well this method performs in the case in which the system is a bit more complex and more realistic, and for which we already have the right answer. So these plots are just, you'll recall the metallicity gradient plot from the Adrian Price Willen et al. 2020 paper. And on the right of that is my analogous plot that I made for the simulated galaxy M12Q. So what I want you to see here is that the qualitative trends are the same, which makes me hopeful that I can redo this analysis for the simulations and then compare those results to the observational results already found in the literature. So to summarize, the overarching goal of this project was to create toy data, observe them, and then implement several different data analysis methods and see how they compare. We really got only to like the implementation part of it this summer since it was only 4 weeks. But the method that I spent most of my time on was orbital torus imaging, which again combines kinematic and chemical information, allowing us to use more of the current data that we have thanks to new surveys like Apogee, with fewer assumptions in that you don't need to know what your survey selection function is, nor do you need the second moment of the velocity distribution like you would in genes modeling. So looking towards the future, I want to ask myself, how does adding observational noise or biases affect our results? And if I consider a selection effect, do I recover in fact that the results are unchanged in that case? Also, what can we glean by applying this method to simulation data, more realistic simulations like the fire cosmological simulations, and seeing how they compare with real life results? So thank you guys. I want to give really huge thanks to like Juan and the mentors, not only on this project, but like just in the summer school, and to the cohort. You guys made it so fun. And thank you for the Flatiron Institute for having me and making it able to do fun science with cool people.
Great talk. Tanya, you always.
I'd like to get in first. So yeah, this is really interesting, and I can see, that the orbital torus imaging has fewer assumptions than the traditional methods for recovering the galactic potential, and you've already started to look at as you're redoing the Bayesian analysis, you're already starting to look at more complex potentials. So this is mainly a suggestion for future work. Along those lines, we've recently been able to measure galactic accelerations using pulsar timing. And so it'd be interesting to compare, and so that's actually time series, very precise time series observations to directly measure an acceleration instead of approximating an acceleration from velocity dispersions using, conventional methods. But it'd be interesting to compare to see, in this particular case, the main assumption would be the phase mixing, right? I gather.
Yeah, definitely. There's so much, like so many different places you could take this project. I'm like excited for all of it.
Yeah, that was great. I'm just wondering, like, physically, why is there this correlation between actions and metallicities?
So when you're, okay, I'm gonna go back to the slide that has the diagram that I drew. I think when you're looking at the blue circle, it's like there's no dependence on the actions there, but when you're in the incorrect potential, it'll start, you're like imparting this metallicity or metallicity depend or angle dependence on the metallicities. I don't know if that answers your question or if I misunderstood it.
The plots from the original paper, like there's definitely like a gradient as you like go outwards, and yeah, I'm just curious, like why?
That's a good question. I just know what I see, that it's there and that it does correspond to the difference in like Catherine.
Like to throw this back to the students. Why? You guys figure it out. No, really. What are we looking at there? Think about the last talk and this talk. An age? How would age go? Go.
Should old stars are metal poor, right? And so they're going to be heated if they are dynamically heated from the disk off of their circular orbits, then their actions will be different.
Yeah, great. So where's the circular orbit in this plot?
At the center.
Yeah. So it's the.
So those are young stars in the middle, and then you're looking at older stars on the outside.
Yeah.
Those orbits.
Yes. So Francisco's talk, right? We started with the Udapan's question. Those thicker disk stars are the outside, and the thin disk stars are the inside here. You know and the high metallicity were closer to circular, and the low metallicity were further from circular. Aha. Correct.
Thank you.
I wanted to ask you, you had this, I think you just had the slide up there with the circle and the ellipse and the different potentials. Mm-hmm. Yeah. So how different is the potential that you used for the right-hand plot then? Because I use different potentials to compare, but usually I'll take two different potentials that have different functions, but both were fit to the data we know about in the Milky Way, right? So then they end up sort of being similar, but they're not similar. But how did you choose a different one? How different is it?
So it doesn't have a different functional form, although I do want to explore when you add a quartic term onto this simple harmonic oscillator potential. What I changed was the value of omega. So I made there was at one point I made it 2. This is 1.75. So it's scaled differently, but it is the same functional form.
Okay. So you changed it from like a 2 to a 1.75.
Yeah.
Okay. All right. Thanks.
Yeah, so I have a quick question. Can you go back one slide? Maybe it's the slide where, yes, this slide. So it's clear from this slide that not all elements are created equal for orbital torus imaging. So you use metallicities, which I assumed you faked the metallicity, but going forward, what are you planning on doing? Multiple elements? Are you just planning on sticking with metallicity? Or where do you plan on going?
Yeah, I think I'd like to consider the different metallicities. Like you said, there are different ones here, and there are different ones like let's say carbon or nitrogen. They obviously have different trends from each other. But that's something that I'd like to look into the future. I'm not exactly sure how yet.
I'm really not good with the microphone, it seems. Do you have a sense of how substructure would alter this? Like if you have clumps in phase space and or metallicity space?
I'm not sure. I don't have a good answer for that.
Good question and a good answer.
But I would love to look into it. That's one of the questions that I'd like to add to the to-do list. Really good questions. Thank you.
I like the second answer. That's a really good one. Oh, great question. I want to look into it. That's good. And then the my other one, very deep. I spent the whole talk wondering why you'd chosen to call it schmeddlessly.
Well, we like messed around with schmagnesium and like schmanganese, schmabundances.
Yeah, all of us had the same question, right?
No, there's an answer to this. It makes Emily laugh every time, unfailingly.
She got it.
That's the question I can't answer.
Mika's probably been wondering that the whole summer.
No, Mika knew every time she heard Emily, like in the back of the room when she was talking about it.